because it's divide and conquer, like we discussed yesterday, we use recursive algorithm. And generally, in most cases, we say that Quicksort is fastest. But after seeing the algorithm, you will know that the worst case of Quicksort is not n log n. It will be n square. But mostly, the worst cases are happens rarely. But generally, uh, we see the average cases, which turns out to be mostly used. So Quicksort is the fastest algorithm in most situations. The idea here is very simple. When we are given an unsorted list, we'll select a pivot element and we'll move all the elements that are less than the pivot or key element is nothing but a random element. You can select the first element, you can select the last element, or you can select the element that is present in the middle of the array. Actually, there are different strategies and probabilities of selecting the pivot element. So there are so many studies of selecting the correct pivot, but generally we say we can take any element randomly. So after selecting an element, we call that as pivot element or key element. We and we will place that element in the middle of the array, and we will move all the elements which are less than the pivot element to the left side of it, and all the elements which are greater than the pivot to the right side of it. So I will show you. You can see the picture. After selecting a pivot element, we will move all the elements which are less than the pivot to the left side and greater than to the right side. Here we are using the swapping technique. We'll go through it in 5 minutes. But let's try to see it in a rough. Let's use pen and paper and try to see it. Let's take an array. Let's call it as L. It's an unsorted array, a random array. And I'm selecting 4 as my pivot. So 4 will be somewhere in between, and all I'll see whether I'll go through each element in the array and I'll compare it with the pivot element. I selected 4 as pivot randomly. There is no logic behind it. So first I'll see whether 8 is greater than 4 or not. Yes, 8 is greater. I'll compare 4 with the first element, 8. 8 is greater than 4, so I'll keep it on the right side of 4. 0 is less than 4, so I'll keep it on the left side of 4. 5 is greater than 4, so I'll keep 5 on the right side. In a similar way, I'll do it for all the elements. If you observe, 4 is our pivot element, and all the elements that are greater than 4 are on the right side, and all the elements that are less than 4 are on the left side. But they are not sorted. The left side array is not sorted, and the right side array is not sorted. But if you observe, 4 got its place of the final position. That means what is the sorted uh, array for the given list? It will be 0, 1, 2, 3, 9. If you observe, 4 got its position. The pivot element goes to its position, right? And what happens if we recursively apply um, quick sort to the left side of the array and right side of the array? If I select 3 as my pivot, 3 gets its place. Let's see. Now I'm selecting 3 as my pivot on the left side of for the left subarray. So 0 is less than 3, 2 is less than 3, 1 is less than 3, and 3 is my pivot. And there are no elements which are greater than 3 on the left subarray. And I have 4. And if I select 7 as my pivot element here, 8 is greater than 7, so it will be on the right side of 7. 5 is less than 7, so it will be on the left side of 7. 6 is less than 7, so it will be on the left side. 9 is greater than 7, so it will be on the right side. We may not guarantee whether 5, 6, and 8, 9 will be sorted, but 7 will get its position. Here, if you see 0, 2, it is not sorted, but 3 got its position. In the final array, 3 has the index 4. Here also, 3 has the index 4. So every time we are selecting a pivot, the pivot element it is getting sorted. So if we apply this recursively, that means we can sort the array. There are two ways you can have a new list which contains the left subarray and right subarray, and we can add the middle. Let's see that case first, and then after that we will try to simplify our algorithm a little more, and we'll try to sort it in place. I'm going to write a function for quicksort, and I'm going to do this till the length of the array is 1, because if we divide as as we saw yesterday, we divide it till the length of the sublist or subarray will be 1. Then we'll return the array, because by then our array will be sorted. I'm I'm going to select my pivot. I told that I want to select the pivot randomly, but this should happen every time when the list is uh, when the list is divided into sublist. So I cannot tell it to randomly take an element every time. So you can take the first element. You can simply take the array's first element if you want, but you can otherwise you can take the last element, or you can take the middle element. So I think the middle element will be fine for most cases. So I'm taking the middle element as my pivot. So I'll divide the length of array by 2. I'll get an index. And so I'm accessing that element, and I'm storing it in a variable called pivot. Now what will be my left subarray? My left subarray uh, will be all the elements which are less than the pivot. So I'm going to add all the x from the array and I'm going to keep a condition that x should be less than pivot. So I'll have a left sublist where we'll have all the elements which are less than the pivot. This is simply uh, a for loop. You can expand it if you want. This line here is equivalent to uh, I'll simplify it. I think you'll understand this. This line here is nothing but it is equivalent to this. One minute. There's a name for this. I'm searching about it. Actually, these are very useful while you are coding. You can simply okay. I'll think about it. Yeah. We'll continue to write the code. My right sublist will be all the elements which are greater than the pivot. So the condition will be if x is greater than pivot. So we should add. Okay, this is okay. We are not guaranteed that the list contains unique elements, right? It may contain two sevens or two eights. So in our conditions, we are adding them only if it is greater or less than the pivot. If it is equal to pivot, we are ignoring it, right? So I'll add one more thing in this. I'll add all the elements which are equal to the pivot. So I can simply add the middle. I can keep the middle element because you, uh, you don't see any difference between all the elements which are same. If we have four sevens or five eights, and if we select one eight as the pivot, all the eights will come into our middle uh, list. If x is equal to pivot. Yeah. Now I have three lists now. The left list, the middle list, the right list. The left list contains all the elements which are less than the pivot. The middle list contains all the elements which are equal to pivot. The right list contains all the elements which are uh, greater than the pivot. And after that, if we add the left, middle, and right, we'll get a sorted list. But it is not guaranteed that the left array and the right array uh, are sorted. But the middle elements will be in their position. So what if I call uh, quicksort on the left array and quicksort on the right array? It will again select a pivot. It will again divide the. It will again create a sublist which has elements less than the pivot, and it will again have a middle, and which will have the elements that are equal to pivot. Similarly, it will have a right sublist which will have elements that are greater than the pivot. So I should call the quicksort on left side and right side recursively. So I'll say I'll call quicksort on the left, and I'll simply at the middle, and I'll apply quick sort on the right. Then I think the array will be sorted. Here I'm not doing it in place. I'm using three variables, left, middle, and right. I think this should work. Let's take a random. Uh, let's take a list. Sort of. Well, let's see. I forgot to give the array parameter. Yes, we are getting a sorted list. But uh, but we all know that quicksort is all. If we are using a new array, it is not in place and it is space consuming. The space complexity will be more, and if the given list is very big, so it will take more and more time, and we need more space. We will try to use the quicksort algorithm in such a way that we'll, without using the left, middle, and right sublists, we'll try to sort it in the given array itself in place. And before that, let's discuss about selecting the pivot. You can select the first element or last element, or you can randomize. But generally, we suggest to take the middle element because in a um, average case, the list is unsorted. It is not sorted in the decreasing order. It is not already sorted, but we assume that it is sorted in it is unsorted in a random manner. That is the average case. So we'll select a pivot that is in the middle. Now let's try to do it in place. I want to share some images. Uh, I'm going to use indexes for doing this. First, I'm going to select a pivot. I'll select the first element as my pivot. I think you can see my screen. I'll select P as my pivot element, the first element of the list. And I'll check, I'll ignore all the elements that are less than P. And if there is an element which is greater than P, I'll stop there and I'll store that index. And I'll start from the end of the end. I'll start it from the end of the list. I'll check the last element and I'll search for the element which is less than the pivot. If I find an element which is less than the pivot, and I'll store that index. So here he is representing them with L and G. L is my, I think it's low and greater. So lower will store my element which is greater than P, and G will store the index of the element which is greater, which is less than the pivot element from the end. And after that, I'll swap them. So after swapping, I'll have the elements which are uh, less than the P on left side and greater than P on the right side. I simply keep the pivot in the middle. So every time if you after repeating, till when will you repeat? I'll start from the zeroth element to the last element of the list, but I don't know when to stop it. So what it means when the start becomes greater than the end. Let's say the start is the element I'm starting from left side and end from the right side. So I know that when start is greater than end, that means there's an intersection between start and end, and there will be the same elements which we have already seen. So I'll get to know that I saw all the elements throughout the list. Now I can swap here. So I will simply swap it after the elements which are less than the P. Now the P gets its final position. Like we saw, the pivot gets it position correctly. So for this we are choosing the first element. This is a unsorted random list. We'll select 66 as our pivot, and from the left side of the array we will find an element which is greater than 66. 99 is greater than 44 is not greater than 66, so we'll increment. 99 is greater than 66, so we'll stop here. And in the same way, we will search for an element from the right side which is less than the pivot. So 33 is less than 66, so 33 is my uh, I'll store 33 in an index, and now I'll swap these both 33 and 99. I'll continue the same process till start and end intersect. So now again I'll search for an element which is greater than the pivot and less than the pivot, and I'll interchange them. So now my start will be 33. After 33, I'll search for an element which is greater than 33. And from the back, I'll search for an element which is less than 33. And I'll swap them. I'll do the same process till start and end will intersect each other. Now let's try to convert this into a code. already used quicksort, so this time if I like this, it will take an array and it will also take low and high or start and end. And in the while I'm calling quicksort, I'll simply say start as 0 and end will be the length of the array because we are starting from the first element and from left side and last element from the right side. And I'll continue this process till start is less than end. Once it is uh, once start is greater than end, I'm going to swap them. For the pivot, I am last time we selected the middle element. This time I'll randomly select an element which is end. End will be the last element from the array. And my left will will be start, that is, and right will be end. End is actually the length of the array. So indexing will have it will start from 0, so I should subtract 1. And now I'm going to search for all the elements which are greater than the pivot and less than the pivot. I'm going to increase the index of left till I find an element which is greater than the pivot. So it should the left should be less than or equal to right because once it gets intersected, we need to stop. And arrays left should be less than pivot. If it is less, I'm ignoring it. I'm ignoring it and I'm increasing left. I'm incrementing left. So after completing this while loop, we'll get an index of an element which is greater than the pivot. I'm storing it in the left. In the similar way, I'm going to do it for the right. And actually, right starts from end, so I have to decrement it. And this should also follow the same rule. Right and left should not intersect because once they intersect, I have to swap them. Arrays right, and this should be greater than the pivot. Then we are ignoring it, and if it is less than the pivot, I'm storing it. So I have to decrement it here. Now I have two uh, indexes, left index, right index, which are uh, greater than and less than the pivot respectively. I have those indexes. Now I have to swap them. And we should also know whether left is less than right or not. It should be like that always. So every time whenever we are doing a process, this the left, right, or uh, the start and end, they should never intersect. If they intersect, we are going to see the same elements and we are going to arrange it again and again. So the loop will never end. If left is less than right, we have to follow, and or it can be yeah arrays. I have to swap arrays left with arrays right. Left is the index which is greater than, so it should go to the right. Yeah, and arrays right to arrays right. and arrays left. Now I'm again following this procedure while selecting the pivot, and I have to increment left once again and decrement right once again, because this process should continue again and again. So I'm going to decrement left, sorry, increment left and decrement right. Yeah. Now we have to move the pivot element to middle. Now we swapped the left element and the right element, but pivot here we selected the last element as my pivot. But when we selected right as my last element, so we never used equal to also here. So I have to keep my right pivot element to its position, and after keep I have to keep it in such a position that all the elements on the left side of the pivot should be less than pivot, and all the elements that are on the right side of the pivot should be on the right side. So I think if I simply move my pivot, that is the last element, to arrays left, that will be done, because arrays left is the biggest greater element from the left side when we compare to pivot, that is in the left element, right? So if you simply swap it with the pivot, our job is done. Yeah. Now I have to apply quick sort for the same, but I need not apply it for the right side of the array. Quick sort of the array will be same, but I'll change the uh, start and end. So this will sort the left part, because uh, at the index of arrays left, I kept my pivot element. So uh, this indicates I'm applying the quick sort for left subarray, and now I should also apply quick sort for elements that are on the right side. So I have to change the start. Start will be something left plus one. I'm ignoring left, and the right will be end. And here I need not. So this line will sort the right side of the sublist, and this will sort the left sublist. Actually, we can reduce. We use extra variables like start and, because generally we'll sort the whole array. Nobody sorts an array. Nobody says uh, nobody gives an array or an unsorted array and says ask you to sort first five elements of it. So I think instead of left and right, start and end, we can simply use all the same variables. We can either use start and here also, or left and right here also. Okay. Anyway, let's check whether this is working. We say, Use the name not same. Okay, sorry, we have to give two arguments, right? My start will be 0 and my end will be length of the array. We got the index of top range. So my end will be okay. End is length of array. It is using length of array. So I gave end as length of array, but here I am accessing the last element using a. I'll simply write -1 here. I think it's better if we subtract the right. We'll write -1 here. Now we can use length of L -1 will be the index of last element of the list. That is 9. Why is it taking so much time? I think one of our conditions may miss an equal to or greater than because it is running so it is taking so much time. It may be a infinitely. Let's debug it. You have to do this till start is less than n and our pivot is the last element. Yeah, this is arrays left and arrays right should be okay. Let's debug it using Python tutor. I'm unable to find where the error is, but our logic is correct. So let's proceed. Yeah, we are getting an infinite loop somewhere. Give me 2 minutes. I'll find where the error is. Yeah. Here we are saying that when left is less than right, I'm shifting them, but it's not the case. Every time left will be less than right, but I have to interchange when they intersect, right? So when left is um, less than right, I'll ignore it. But otherwise, when they intersect, then I have to swap them. I think this should. Maybe refresh this page. I think there is some problem with this collab because this is just a function. It shouldn't take this much long to execute it. I'll create a new collab and I'll show you one. Yes, we'll use otherwise we'll use the Python filters. Yeah, and I'll call the function and we are doing it in place, so we are not returning anything. The array will be sorted. So I'm just printing L. Yeah, you can see our arrays are sorted, but I think there's some problem with my collab. Maybe few more people are using it. Okay, let's discuss about the time complexity. And again, we'll see to check the time taken by quick sort in best case, worst case, and average case using the time module. I think by then the collab file should work. Otherwise, I'll create a new collab file and let's continue the session. Uh, for partitioning or selecting the pivot, we are taking uh, a linear time O of 1 because we are selecting it randomly, or we are either selecting the first element or the last element. So there is no time taking there. But every time we are using recursion for a half. Yesterday we divided our list into two halves in merge sort. In quick sort, we selected a pivot, we kept it in the middle, or we kept it in the in its position. And now also we have two sublists, a left sublist, a right sublist, which almost contains same number of elements. Or we have to apply the same uh, iterations for it. But what is the best case for a quick sort when the list is already sorted? Because we'll will not find any element that is greater than the first element to store it in the left index. So it will check all the elements, and since we have no element which is greater than the first element, we'll simply increment it. And for the second element, it will search all the elements which are greater than it on the right side. Since we don't have anything, there is no need to swap. So that's the best case. And the worst case is when the list is sorted in the reverse order. So when the list is sorted in the reverse order, it should check all the elements and it will find the list element in the last position. So it should swap it. So it will take n square. And I want to also discuss about stability of the algorithm quicksort, because in sorting, if two items are equal, a stable sort keeps them in the same order as they were in the beginning. Quick, Quickshot doesn't do this because every time when it sorts, it might flip two same elements. Because in the first approach, we took a variable named middle, and it stores all the elements which are same, but we don't know whether it is keeping it in the stable manner or not. It can keep it it can keep two sevens in any order in any order. It is not the same order that is given in the question. Or for example, if I give you one two sorry 2 3 1 4 4 7, I have two fours in this list, and there is no guarantee in quicksort that the first four that appears in the question may appear first, or it may appear second. Stability here depends. Uh, if the first four appears only in the first place, then it is called stable sorting. But it is not guaranteed in quicksort because we are using variables, or we are using start and stop, and we are swapping them constantly. So that is not guaranteed in quicksort. But we can implement quicksort in place. So we can say that it is not stable, but it is in place. Till now, if you have any questions, you can write them in the chat box. And if time permits, I want to show you the time complexity. I'll copy paste the same code here and maybe now, yeah, I don't know why, but now we can faster. Sorry, we should not print because we are not returning anything. We have to just print our list. Yeah, very okay. So actually, this is very complex. You may forget the algorithm, or you may find all the while loops and the conditions that we get. Even I got confused here. The initially when we got an infinite loop, that is what we have did. I used left is less than right. I swapped the elements when left is less than right, and it is an infinite loop because left will be always less than right uh, until the list is sorted. So every time if I swap like that, the list will be never sorted and it will find a way and the loop is continuing like that. So I recommend you to use Python tutor whenever you find difficulties because debugging is also very important while you code. Okay. You can send me a mail if you have any doubts, or you can contact me. You can type your question in the chat box. Anything is fine. And for calculating time, it is, and if you want the same code in Java, I'll share it. Okay. I have sent it in the chat box. So you can simply import time module, uh, store the initial time, quicksort the given list, store the final time, and if you subtract final time with the initial time, you will get how much time is taken to sort. Okay, guys, then have a nice day.